Hi everyone. I'm very happy to have Professor Chao Xiaofeng here to give us a talk. Professor Chao Xiaofeng is an assistant professor in computer science and electrical engineering at Stanford University, and her current research has been recognized through the ACM Doctor Dissertation Award and the Microsoft Research Faculty Fellowship, and also the MIT Review 35 Under 35 Award. And let's enjoy her wonderful talk.
Great, thank you for the introduction. And yeah, everyone feel free to ask questions in the chat or after the talk. So today I'm going to be talking about tackling distribution shift through different approaches, through pessimism, adaptation, and anticipation. And I guess to start with a little bit more of an introduction, I actually primarily study the application of robotics, and I'm interested in how we might be able to develop broadly intelligent behavior in these robotic systems. And of course, there are a number of challenges that come up when you actually want to build a robot that can act intelligently, including things like perception, control, and so forth. And so what I'm going to talk about today is somewhat inspired by some of the problems that we run into in robotics, and also arise in machine learning and computer vision more broadly. And in particular, the motivation for what I'm going to talk about today is that machine learning works quite well. We've seen really impressive applications ranging from image classification to machine translation and so forth. However, it works really well when you can collect a very broad training distribution and when the test distribution, the data that you evaluate on, is within that broader distribution. And so a core assumption that arises in machine learning is that our training distribution matches our test distribution. And unfortunately, in many practical applications, including applications in robotics, applications in computer vision, and a number of other applications, this assumption no longer holds. So to hopefully try to convince you that distribution shift matters a lot, I want to give a few examples of distribution shift before talking about how we can actually solve it. So I'm going to start with two examples. The first example actually comes from robotics, where we want to be able to take an offline data set of behavior from a robot, and we want to use this data set and run reinforcement learning on this data set in order to get the robot to do the task, such as opening a drawer. And unfortunately, there's a distribution shift between the policy that's represented in the data set and the policy being optimized. And as a result, if you actually don't account for this distribution shift and you try to optimize a policy, then you get a behavior that looks like this, where it isn't actually, in this case, successfully closing the drawer right here. And it actually gives you a policy that's quite unsafe. So this is one example that I care a lot about, but there are a number of other really important examples as well. So for example, back in 2009, Google put out a paper on trying to predict flu incidents from search queries so that you can try to get ahead of potential spikes in flu and so forth and understand the incidence. And in their paper, they reported 0.97 mean correlation with CDC data, which really kind of, on paper at least, sounds really great. It seems like we might be able to use search queries instead of on-the-ground data to predict this sort of incidence. However, a number of years later, this same system was predicting double the true incidence of the flu. And this happened because there's a distribution shift over the course of training. It may have also been picking up on spurious correlations earlier that didn't hold in the future. And other works have also shown that language models can be susceptible to the same kind of distribution shift when testing them over time. So these are two kinds of distribution shifts. Distribution shift can also arise from different domains and different subpopulations. And in particular, if we consider a task of online content moderation, if we want to try to make the internet a slightly better place and predict whether or not a comment is toxic or not. On a typical data set, you can get around 92.2% test accuracy, which again sounds great, and it seems like maybe this is something that we could use. However, if you look at the accuracy on non-toxic comments that mention the Black demographic, the accuracy drops to 69.2%. And this is a problem not only from the standpoint of fairness, but it's also a problem that if, for example, you had a distribution shift in the incidence of these kinds of comments, or if you kind of try to apply your system to a population with different demographics, then your system would perform substantially worse. And one more example, just trying to show a very broad number of examples here, is this task of molecular property prediction, where we want to be able to predict the biological activity given the structure of the molecule. And this can get around a 34.4% average precision on test molecules from a broader set of training scaffolds. However, if you then test on molecules from different scaffolds, from held out scaffolds, this precision drops substantially. Great, so hopefully I've convinced you that distribution shift is important and matters and actually leads to meaningful drops in performance in real machine learning systems. And if you're interested in this problem, these two data sets are an example of the data sets in this WILDS benchmark that really is trying to focus on this distribution shift problem. It was a large effort led by Pangwei and Shiori, who really did a fantastic job putting together these different data sets by talking to domain experts and kind of collecting something that leads to an evaluation that actually matters in real world distribution shift problems. So I'd encourage you to check it out if you're interested, and Pangwei and Shiori are both kind of eager to have feedback from the community. Okay, so that's the problem of distribution shift. Now, how do we actually go about tackling distribution shift? Can we build machine learning models that don't make this assumption that our training and test distribution matters? So in this talk, I'd like to talk about 3 broad tools that we can use to tackle distribution shift. The first is pessimism, the second is adaptation, and the third is anticipation. And I think that actually breaking it up into these 3 categories is quite useful because it allows us to think about the set of tools that we have available to us and also categorize and understand both the benefits and the limitations of existing approaches, because each of these 3 categories has their own set of assumptions and also their own sets of benefits. And kind of as we go through the talk, we're going to be introducing more assumptions about the kind of distribution shift problem that we have. But as a result, we'll be able to get better performance in scenarios where those assumptions hold. Okay, so let's first start by talking about pessimism. And the idea behind pessimism for tackling distribution shift is to prepare for the worst way in which the distribution can change. And in particular, oftentimes we never really know exactly how the distribution is going to change. And so what we can do is we can consider all the possible ways that it can change within some set and optimize for the worst case in that set. And so that's actually exactly what the kind of intuition behind this really beautiful framework called distributionally robust optimization, where we want to optimize for some model such that the worst case distribution within some uncertainty set is minimized. And so in particular, now the key choice here is how do we actually define this uncertainty set? And in particular, this uncertainty set is telling us what possible ways do we think that our distribution might change. And then we'll optimize for the worst case within that uncertainty set. So there are a number of different ways that we can model this uncertainty set, and there are a few different ways that that have been popular in the literature. One thing you might notice is adversarial training is a special case of this. However, this won't prepare the model for more natural shifts in the distribution. It'll allow you to kind of essentially prepare for adversarial attacks. And some other common choices for the uncertainty set are as follows. So one way that we can define the uncertainty set is this kind of ball around our empirical distribution P that's within some epsilon Wasserstein distance from our empirical distribution. Another is this kind of popular and kind of very old notion of conditional value at risk, where we consider our uncertainty set contains all distributions over some portion of our training data. This is essentially going to be optimizing for, instead of like the average case, we're going to be optimizing for some percentile so that we can be more pessimistic about the performance that we're optimizing for. And then the last choice that I'll mention here is called group DRO, where we assume that we have different domains in our data set, and that the distribution is going to change just in terms of the proportions of those domains at test time. And then therefore what ends up being kind of the worst case distribution there is the distributions with all of their mass on one of those different domains, in particular the domain that your model is currently doing the worst at. Okay, so this is a really nice framework for trying to be robust to distribution shift. However, there's also some pitfalls with these approaches. So it's a beautiful principled framework, but for these two approaches, which I will call or refer to as joint DRO because they are trying to be robust to this kind of joint distribution, they end up having a very large uncertainty set. And as a result, you can be kind of somewhat too pessimistic about the kinds of distribution shifts that you will see at test time. And then likewise, this actually kind of almost on the opposite end of the spectrum, group DRO can be quite effective when you have different distribution shifts over the domains, but it does require detailed knowledge during training that your data corresponds to each of these domains. Okay, so what I'd like to talk about next is an approach that we can use that still leverages this principle of pessimism, but tries to get around these two limitations of joint DRO and group DRO. And in particular, we're going to kind of focus in on one form of distribution shift that's caused by spurious correlations, where during training, a large portion of your data has the label kind of correlating with some spurious attribute. And at test time, more of your data doesn't have that spurious correlation. And so in particular, some examples of what this looks like includes the content moderation task that I mentioned before. It also includes this water birds data set where you want to predict whether the bird in the foreground is a land bird or a water bird, which spuriously correlates with the background being land or water in the training data set. We'll also look at Celebe, where you want to predict hair color, and the gender is the spurious attribute. And lastly, we'll look at this natural language inference task where you're trying to predict entailment or not, and your spurious attribute is whether there is negation. Okay, so each of these are cases where there's these challenging spurious correlations in the training data set, and we want to be able to do well at test time on data points that have this spurious correlation, as well as on data points where this spurious correlation does not hold. And so the first thing that we did, of course, is actually evaluated what these previous approaches do on these data sets. And what we can find is, in terms of average accuracy, all of these methods are doing pretty well. And we also find that group DRO, which is trying to optimize for the worst case group, where a group is defined as the attribute and the label pair, we see that group DRO does quite well in terms of the worst group accuracy. It does well when the spurious correlations don't hold. However, it requires labels of this spurious attribute during training on all of the training examples. So this means it's going to be pretty expensive to actually label these spurious attributes in practice, and also may not apply in settings where we don't actually know the spurious attribute in the first place. Okay, and then unfortunately, joint DRO, which makes less assumptions than group DRO, does much worse. It shows really little gains on over ERM on this robustness metric. Okay, so then the key question here is, can we essentially get much closer to the performance of group DRO without requiring knowledge of this spurious attribute during training? So we kind of first asked, well, why doesn't joint DRO work for these spurious correlations? And what we found is that if we plot essentially the fraction of these minority data points where the spurious correlation doesn't hold, if we plot the fraction of these points that are upweighted by joint DRO, we do see that it does kind of upweight them more and more at the very beginning of training, but then really prioritizes them much less later in training. And essentially, it's much less directed at these minority data points than group DRO, which would essentially be kind of prioritizing these data points at a much higher level. And so that means that maybe to tackle this problem, we can essentially like really try to identify these examples where the spurious correlations don't hold, and then prioritize exactly those examples. Okay, so that's essentially going to be our high-level approach, but unfortunately we don't have labels for when the spurious correlation doesn't hold. However, the key insight that we can make is that standard ERM performs poorly on these examples when the spurious correlations don't hold. And so what we can do to identify these examples is simply train a model with empirical risk minimization and find the data points for which it misclassifies and then prioritize those examples. So that's exactly what we're going to do. We're going to train this identification model with ERM. It's just going to be a standard neural network. We'll then compute the error set, which are examples that this model misclassifies, and then upsample these examples in our training data set and train a final model on this modified training data set. And that's it. So this kind of this two-stage approach. So we refer to this as just train twice, or JTT. And it's quite simple, and the number of hyperparameters is actually also quite small. The main hyperparameters is just corresponds to how much early stopping you do for this first model, as well as how much you upweight these examples by, the coefficient with which you upweight these examples. And then otherwise, these two models have the same exact architecture and so on and so forth. Okay, so how will this approach work in practice for solving these problems? We compare just train twice to empirical risk minimization and joint zero, and also an approach called learning from failure, which is a representative approach with very strong results on these kinds of problems. And for a fair comparison, we tuned all of the methods, including JTT, including ERM, and these two methods, with respect to the worst group validation loss. Unfortunately, this does mean that we are implicitly using knowledge of the spurious attribute in the validation set. However, we're not using it in the training data set, and that kind of leaves something to do in future work. Okay, so how do things do? First, we see that JTT gives us a 10% improvement in worst group accuracy on 3 out of the 4 data sets. And on the 4th data set, we can also see around a 2% improvement. And second, we actually see that on 2 of the data sets, JTT is actually comparable to group zero. But of course, it doesn't require knowledge of the spurious attribute on any of the training examples. So this is pretty nice. It means that we essentially have a method that can help us start to be much more robust to spurious correlations. Now, to dig into this a little bit more, we wanted to ask what data points JTT identifies. And so for this, we asked 2 questions. The first question is, what portion of this error set that we're identifying from the first model actually corresponds to minority examples where the spurious correlation doesn't hold? And what we find is, if we look at the precision of these data points in our error set compared to the empirical rate, we overall see that it is much higher than the empirical rate. So 5 from 45, 28 to 38, and 10 to 72%. We don't see the same trend with SLEB A, and this is because because of kind of a minor detail in terms of how minority groups are defined. For the actually smallest group, we do actually see an increase in the precision. Okay, and then the second question we ask is, what if we actually remove the majority points and the minority points from our error set? How does that actually affect downstream robustness? And what we find is the following. So the blue bar here is showing the accuracy with the standard JTT method. Orange is showing what happens if we take the JTT method, but we manipulate the error set and remove all of the majority examples and only keep in the minority examples. And then the green bar is the same thing, except if we pull out the minority examples. And surprisingly, one of the things that we see here is both majority and minority points are helpful. We see a drop in performance both when we remove these 2 points. And the reason for this is, if we actually visualize the examples in the error set, and in particular, if we visualize the majority points that it identifies from the waterbirds data set, which corresponds to waterbird with water background, these are what the images look like. And we see that the ones in the error set have a somewhat ambiguous background. So there is water in the background, but it's not obvious that it's a water background versus a land background. Whereas the ones that aren't in the error set are ones that very clearly, or at least much more clearly, have a water in the background and have a water background. And so this suggests that the what JTT identifies is not only examples where the spurious correlation doesn't hold, but also data points where the spurious attribute is difficult to detect or otherwise ambiguous, or just doesn't exist. Okay. Great, so the takeaway here is that we can achieve robustness to spurious correlations by prioritizing these hard data points, even when we don't have knowledge of the spurious attribute in the training set. Now I'd like to take a little bit of an aside and look at the reinforcement learning problem that I mentioned before, and just see if we can use pessimism for this reinforcement learning problem as well. And really the key idea here is that we can be pessimistic with respect to the value, or the Q value, of out of distribution states and actions. And essentially what we're trying to do is we're trying to have the policy avoid visiting states that are out of distribution, because it will likely not make accurate predictions on those out of distribution states. And in this way, reinforcement learning is actually a little bit easier than supervised learning, because we can actually control the distribution of states that, the distribution of images that the robots use. Okay, and it turns out that if you look at 3 recent methods, including some methods from my lab, a lot of them actually have this principle of pessimism, where they try to minimize the Q function on out of distribution actions, they add a reward penalty when the model is uncertain, or minimize the Q value on out of distribution states and actions. And so this suggests that pessimism does seem to be actually, I guess I should say, these are all like methods that are actually kind of close to state-of-the-art performance on popular offline RL benchmarks. They all come with theoretical performance guarantees. And so this suggests that pessimism can be quite effective for reinforcement learning. And also coming back to the example that I showed before, if we take one of these methods, actually this second example right here, and combine it with models that can handle perceptual inputs and run it on a real robot, the robot can actually successfully solve the task. And you can see the robot successfully closing the drawer here. And this policy has a 76% success rate, which is much higher than if we didn't incorporate pessimism into this offline reinforcement learning problem. Okay, so really the takeaways of this first part is that pessimism is a really powerful tool for addressing spurious correlations and policy distribution shift. It generally makes very few assumptions. The assumptions that we saw in JTT were very minimal, and likewise in the reinforcement learning examples. Typically the strongest assumption that you'll see is knowledge about this uncertainty set. And often these methods are usually possible to analyze theoretically, which also means that we might be able to get guarantees out of them. Okay, so now I'd like to move on towards another tool for tackling distribution shift, in which we're going to try to introduce an additional assumption, and as a result be able to get a more powerful method for addressing distribution shift. And this is this idea of adaptation. And in particular, our goal is going to be not to just be robust to the distribution shift, but actually try to adapt to the distribution shift. Now, why should we actually adapt? So I'm just going to show a really simple example where, say we have kind of 2 parts of our distribution. In one part of our one group of our distribution, the data looks like this. In one part of our distribution, the data looks like this. Or you could also think about it as like the distribution shifting from group 1 to group 2. In this case, approaches that use pessimism can't solve this problem because there doesn't exist a single decision boundary for these data points. So anything that tries to be robust or invariant to this form of distribution shift simply won't give you a viable solution. And so this is where ideas like adaptation can come in. So if we see essentially enough groups at training and we can form a pattern of what the kind of meta distribution over these distributions look like, and we see some unlabeled data points from one part of the distribution, then we should be able to predict what the decision boundary should be. So for example, if these are your data points right here from a third part of the distribution, then you can reasonably ascertain that the decision boundary is right here, and these are positive examples and these are negative examples. And of course, potential solutions to this problem include things like domain adaptation, transfer learning, meta learning, and so forth. And the problem setting that I want to kind of focus on here in this talk is a federated learning problem setting. And I'll give an example in handwriting recognition, but we also have examples on more natural images in our experiments. So say, for example, we want to be able to recognize the handwriting of different users. This is from the federated extended MNIST dataset. So it contains alphanumeric characters and written by different users. And you want to be able to, of course, predict the character from the image. And in this setting, there are possibly many different target domains because there's many different users. And you also really want to be able to adapt on the fly with minimal data, with minimal labels and minimal compute. And so, for example, things like domain adaptation might be rather unwieldy to apply here because you would need to, for example, actually unsupervised domain adaptation methods would actually need to kind of train on both the training data set and the test domain in order to generalize well. And we're more in the setting of domain generalization here. Okay, so how do we solve this kind of problem? I guess first I'll mention that we're going to assume that we're not going to have any of the labels at test time. We're just going to be given a small sample of data from one of the users. And we want to be able to use that to adapt to the distribution of that user and predict the correct label. And so in particular, at test time, we're given this unlabeled data from this new test domain. It might be a new user, it might be a different time of day, or a new place. And so in the character writing example, it might be this kind of set of images that correspond to digits from a new user. And then we want to use this unlabeled data to adapt our model and infer the labels on all of the examples that we were given. So the assumption here is that the test inputs from one group are available at test time, either in a batch like here, or at least streaming such that you can kind of accumulate these images and adapt to them as you get them. Okay, and then at training time, the way that we're going to approach this problem is trying to separate the data into these domains, for example, into different users, and then train a model such that it can adapt to an individual user with only unlabeled examples from that user. And then, of course, comes the question of how do we adapt with unlabeled data? So we're going to solve this problem, we're going to take a meta-learning approach where we try to train a model such that when it's seen unlabeled examples, it can perform well. And so there are a few different ways that you could do this. One way that you can do this is to use a meta-learning algorithm like MAML, except instead of running gradient descent in the inner loop with a standard loss function, you actually learn a loss function that can be applied to unlabeled data points and can be used to update your model. And so you're learning both the initial parameters data as well as your loss function such that this unlabeled adaptation gives you a model that is accurate on that user or on each user in your training data set. Another approach that you can use that's perhaps a bit simpler is to perform this context-based meta-learning approach where you simply just take as input all of the unlabeled examples from the user to produce some context variable and then use this to predict the label from the test example. And in the simplest case, this second approach can essentially just set the context to be your batch norm statistics, where you compute your batch norm statistics using the unlabeled examples from that user. And then when predicting the label for a new example, you just pass it through the network with those computed batch norm statistics. And this isn't quite the same as standard batch norm, because in standard batch norm, you typically don't want your batches to be correlated. You randomly sample them across your training data set. And so in this case, we're actually specifically creating correlated batches such that the model can leverage that, and also providing it with correlated batches at test time using unlabeled examples from your user. Okay.
Hi, Professor Josephine. Just one small question to be clarified on the previous slide. Sorry to interrupt.
Yeah.
So here in this case, all your data is unlabeled, or just part of the data is, for example, just the test data is unlabeled, or when you use a memo, for example, you only in the inner loop optimization, you use unlabeled loss. So which case are you considering?
Yeah, so all of our training data is labeled and broken down into users, but at test time, we only have unlabeled data, potentially from a new user or from one of your existing users. And so when we use MAML, the inner loop of MAML is using unlabeled data and the outer loop is using labeled data. And at test time, we only get a small batch of unlabeled examples.
I see. Thank you very much.
Yeah, great question. Okay, so we refer to this approach as adaptive risk minimization in the sense that we are kind of adapting to a set of unlabeled examples and minimizing our performance after adaptation to unlabeled examples. And so we compare this approach to standard empirical risk minimization, to the group distributional robustness approach that I mentioned before. Also simply upweighting the groups to the uniform distribution in the case where your groups are imbalanced. And then we also compare 3 different forms of adaptive risk minimization. First, adapting with a context variable. Second, adapting with a context variable where that variable just corresponds to the batch norm statistics. And lastly, adapting with a learned loss with a MAML-like method. Okay, so the first thing we looked at was the federated extended MNIST example that I showed before, where the goal is to adapt to new users with only unlabeled data from those test users. And what we found is that if we measure both the average performance as well as the worst case performance, where this worst case performance is evaluated over different users, we see a 5% improvement in average accuracy from around 80 to 85, and a 10% improvement in worst case accuracy from around 62 to 72. And this worst case accuracy is actually potentially something that we care about a lot if we want different users to be having closer to the same experience. So this is pretty nice. And this is also includes improvement over a federated learning method called QFed average from 2020. Okay, and then qualitatively, if we look at this, say we give an example that looks like this to a model. If you give it to ERM, it's going to predict that it's a 2. And this is in some ways because both because it somewhat looks like a 2, and also because in the training data set, there were actually more 2s than lowercase a's. If we take our method and give it a context of just these 2 examples, then it also predicts a 2 because these 2 examples don't really give it additional information. However, if we give it all 50 examples shown here, then it's able to correctly figure out that this is actually a lowercase a rather than a 2. And the reason why it can figure that out is it sees examples of 2s written like this and lowercase a's looking like this. And is able to essentially kind of disambiguate the way that this user writes a 2 versus the way that they write a lowercase a. Okay, and then beyond the federated extended MNIST setting, we also looked at CVPR and Tiny ImageNet-C. And in this case, we wanted to adapt to new image corruptions. And so we trained using 56 different corruptions and tested using 22 disjoint corruptions that weren't in your training data set. And what we find here is evaluated on both of these, we saw a 3 to 10% improvement in average accuracy. So a 3% improvement on Tiny ImageNet-C and a 10% improvement on CVPR10C. And we also saw an 8 to 21% improvement in worst case accuracy. So overall, we're seeing pretty big benefits by nature of having this unlabeled data at test time and actually appropriately leveraging this unlabeled data at test time. Okay, so yeah, the takeaway here is that essentially a small amount of unlabeled data even can provide a really large amount of leverage for trying to tackle distribution shift. And I guess it's also worth mentioning that like things like domain adaptation, few-shot learning, and so forth also fall within this bucket of adaptation and have also been quite successful at building neural networks that can actually successfully handle distribution shift under slightly different assumptions. Okay, and then the last thing I'd like to talk about briefly is, instead of just adapting to distribution shift, can we actually get ahead of the distribution shift when the distribution shift is happening in a predictable way over time? And most of the examples that I'm going to be looking at here is in a robotics and reinforcement learning setting, but the underlying ideas are also applicable to time series problems, as well as kind of temporally varying computer vision problems. Okay, so we're looking at distribution shift, continuous distribution shift in reinforcement learning over time. And there are prior works that can model this form of distribution shift, including POMDPs. And POMDPs cover this setting, but they're perhaps too general, and getting methods that can solve the full POMDP problem in its full generality is quite difficult. There are also sets of MDPs called Bayes adaptive MDPs and hidden parameter Markov decision processes. And these have hidden parameters underlying the transitions and the rewards, but they assume these hidden parameters are stationary throughout the robot's lifetime. And as a result, it can't actually model the setting where you have distribution shift over time. And so motivated by this, we introduced kind of really a variation on the hidden parameter Markov decision process, which we call a dynamic parameter Markov decision process, where you have these hidden parameters underlying the transition and the rewards. In this case, we're actually defining them to be fixed within an episode, but that the parameters systematically shift across episodes. So how well do kind of algorithms perform with such shifts if you don't actually explicitly account for such distribution shifts? We started by looking at two really simple examples where the goal that we want to reach towards is changing over time, as well as the wind and the velocity. Sorry, the wind and the velocity that we'd like to go at are changing over time. And what we found is three algorithms, including SLAC, SAC, and PPO, all performed quite poorly in terms of performance compared to an oracle that can directly observe how the distribution is changing. So we'd like to try to bridge this gap somewhat. And so the way that we're going to do this is we're going to build upon this notion of reinforcement learning as inference in a graphical model, and essentially augment this graphical model with this dynamic latent parameter that underlies the change in the environment. And so across different episodes, we'll have this latent parameter that can affect the dynamics as well as the reward. And this latent parameter will evolve over time. And so this essentially can means that there is this distribution shift, and it may also be somewhat predictable in the sense that Z does yield Z prime to some degree. And in our method, we are actually going to kind of make this key assumption that it is actually predictable and that we can actually, at least to some degree, predict how the distribution is changing over time. And this will allow us to actually anticipate distribution shift rather than just adapt to it after the fact. And so if we actually formulate the evidence lower bound in this graphical model, we get an objective that looks like this. This equation is rather complicated, but we can actually break it down into three simple terms. This term is just modeling the environment. So it's modeling the dynamics and the reward as a function of our current latent variable. This term is modeling how the latent variable is shifting over time, as and also, of course, the inference process of that latent variable. And then this term just corresponds to entropy regularized reinforcement learning. Okay, so we refer to this algorithm as, or the algorithm that optimizes this objective as lifelong latent active critic. And on the two examples that I showed before, we see that this approach, by kind of anticipating and modeling the distribution shift, is able to substantially improve over these prior methods. And I guess it's also worth mentioning, I didn't mention this before, is that the SLAC algorithm does actually have the capacity to model the distribution shift in the sense that it can try to infer the distribution shift from the observations, but it doesn't actually try to explicitly anticipate it over time. Okay, and then we also looked at more challenging settings, including this Minotaur robot with a continuously varying mass, as well as this kind of 2D world where the wind is continuously varying and there's actually no resets. It's a kind of a fully open world lifelong setting. And in both of these settings, we also see that kind of pretty substantial improvements from leveraging the from actually trying to anticipate distribution shift and get ahead of it. Okay, so essentially by modeling and anticipating this kind of change, we can actually develop methods that can learn amidst this form of non-stationarity. And now I'd just like to end by briefly covering this extension where the distribution shift isn't actually governed by some environment, but is actually caused by other agents. And so the key conceptual change is that now the agent's action can influence this latent variable, not just, it is not just kind of evolving on its own. And now this, essentially you can think of this Z variable as capturing the strategy of the other agent. And that other agent potentially reacting to our agent. Okay, so the way that we're gonna kind of handle this new problem setting is to predict the Z not only from the past, but also from the entire past trajectory so that we can model the interactions and model how our agent can affect the other agents. And we'll look at this in an air hockey example where we're controlling this robot on the left and this robot on the right corresponds to the other agent. And the other agent is essentially trying to shoot pucks at our agent, and our agent is trying to block it. And it's going to be kind of changing its strategy based off of how our agent is reacting. Okay, and so the way this algorithm works is we learn this kind of autoencoder that tries to learn this latent representation of the other agent by predicting the future trajectory from the previous trajectory. And then we're going to train a policy conditioned on this latent representation of the other agent. Or you can also think of this as this latent representation of the current part of our distribution. And then we will kind of take our updated encoder and predict the latent strategy of the other agent and condition our policy and kind of iteratively collect more data and then use that to, again, update our policy and our encoder. And this will involve like repeated interactions between the two agents. Okay, and then I've talked about anticipating change. One interesting thing that comes up in this setting is that we can not only anticipate change, but if we actually optimize for long-term performance over many different interactions, then we can actually optimize to not only anticipate it, but also influence the change in distribution and influence how the other agent is interacting with us. And so, for example, in this air hockey example, looks like the video is not playing too well. If you just apply a standard reinforcement learning algorithm, it's not very good at blocking shots from the other agent. Whereas our approach is, after just about 2 hours of training, it's able to reasonably block shots from the other agent. Yeah, and after 4 hours of training, it's able to, I think, block shots that are at quite a high success rate. Even though the other agent's policy is changing over time. And so quantitatively, we see the success rate after about 4 hours is more than 80% success. And also, if we actually reward the agent for blocking on one side, for example, on the left side, then what it will do is it will actually influence the agent to produce shots that are on the left side much more often than on the right side, compared to an approach that doesn't actually try to influence the other agent. Okay, so kind of the takeaway here is that we can not only get ahead of the shift, but we can not only get ahead of the shift in environments that are changing predictably, but we can, in some cases, actually influence how the distribution is changing over time. So to summarize kind of the entire talk, I talked about these 3 tools for tackling distribution shift. The first is try to be pessimistic about how the distribution is going to change and prepare for the worst case and be robust to that worst case. The second is using ideas from meta-learning or domain adaptation to actually adapt to the distribution shift using a small amount of data. And by introducing this assumption of a small amount of data, you can actually do a lot better, potentially, than approaches that are pessimistic. And then finally, in cases where the distribution is changing over time, we can actually do even better than adaptation by actually anticipating and adapting before the shift even happens, and in some cases influencing the shift. With that, I'd like to thank my students. And if you're interested in working on distribution shift, I'd really encourage you to check out the WILDS benchmark again. It has a lot of really cool real world applications. Even beyond looking at distribution shift, I think that the real world applications and the kinds of data that in it are pretty cool for studying machine learning. Great, and I'd be happy to take some questions.